Good evening. I'd like to dedicate this math video to Bert K. Waits, whom I met in Indianapolis at a National Council of Teachers of Mathematics conference in the early 90s. And after watching his lecture, had the chance to talk to him afterwards and asked him about his calculator involvement. And he shared with me that in the 70s he resisted calculators for the longest time until finally he couldn't anymore, and then he finally embraced them. And to this day, AP Calculus uses calculators and non-calculator versions of their exam, as do the International Baccalaureate Math. They have calculator versus non-calculator. And so it's like people like Bert K. Waits that embraced it and brought people up to the 21st century. So what I gather from him is that he promoted problem solving, motivation, and to adapt to the students' learning styles. And so I'll pick it up from there. So this topic is on decomposition of math, or rather throwing the decomposition into the compost bin. Not to say that Bert would agree with this, it's just my own idea, but I'm just trying to adapt to the students that need a different teaching style, because sometimes decomposition just doesn't work for every student. And if the teacher just says it's a factor, who cares how they factor, right? As long as they factor it correctly. So this method, which would require either guess and check or decomposition, we can get rid of it by doing the following. Whatever's in front of the x squared, non-1 obviously, otherwise we just do it by the factoring. Usual techniques. We multiply that 12 by the constant term 6, negative 72. Notice I don't have an equal sign here because they're not equal. It's not a true statement from there to there. But as we'll see in the proof later on, it does work all the time, if it is factorable. So once we have it in this form, now our challenge is to factor it by the basic factoring techniques. What multiplies to negative 72 and adds to 1? Well, trial and error, we can get that pretty quickly, a lot more efficiently than maybe this one up here. X plus 9, x minus 8. These are equal. Notice here, these aren't equal, because the next step is we're going to, since we multiply by 12 here, we're going to divide just the constant terms by 12. Reduce. These are equal from here to here. 3 over 4, negative 2 over 3. If there is a denominator, which there is in both these cases, slap them on the numerator, or slap them on the x term here, up top. So the 4 comes up with the x, the 3 comes up with the x, and we are finished. These are the factors of this expression. Let's make the numbers a little bigger. 18x squared plus 27x minus 35. Take the 18 away, multiply it by the negative 35. Notice these are not equal. This is just an arrow. Teachers don't like equal signs when they're not equal. So try to avoid those or you'll lose points. Now of course that's a big number, negative 630. 18 times negative 35, so you might have the challenges to come up with the factors of that. But if you're not a calculator, these are pretty easy to come up with, whether you graph it and come up with the roots and see what they are, expanding the domain so you can see them cross the x-axis, or using the quadratic formula in your calculator to help you come up with the factors. If the calculator is not allowed, you might want to fool around with the 18 times 35 instead of multiplying it to 630. Just fool around with the factors until you can see what pair, like say 6 times 7, as we break the 18 to 6 times 3, 35 times 7 times 5, fool around with the factors and see which combination gives us 42 and 15, i.e. what multiplies to negative 630 and adds to positive 27. So we can see it's going to be a plus and a minus. So once we have that, of course, these are equal. The next step, they're not equal. So since we divided by 18, since we multiplied by 18, we'll divide each of these constant terms by 18. Reduce 5 over 6, negative. 7 over 3, positive. And the final step is to slap the denominator up with the x, 6x minus 5, 3x plus 7. And it works. They both work. And they'll always work if the quadratic is factorable. So we don't need decomposition. I'm not saying you shouldn't teach it. We should teach all the various methods, but adapting to the various learning styles, that's one of the things Bert would have did promote, and calculators afforded that one particular one, as we can see with the AP Calculus and IB curriculums. So to make the teachers happy that don't like change, here's the proof that it always works. First of all, to guarantee that it's factorable, we can start off with ax plus b times cx plus d, which guarantees it's factorable because we're starting with two factors. Multiplied out, we get ac plus x squared plus blah blah blah. There it is. So the method says, okay, let's take the ac and multiply it by the constant term. Well, there it is. Of course they're not equal. This is just an arrow, but it's ac bd. Once we're into this situation, we're looking for two numbers that multiply to AC BD and add to AD plus BC. Well, in algebraic form, it's pretty easy to see. It's AD and BC. Sometimes algebra is easier than numerical. So, of course, these are equal, and these are not, but we're just laying the groundwork. So in the next step, since we multiply by AC from here to here, we have to divide the constant term in both cases by AC. Here the A's cancel out, cancel causeway, the C's cancel out, and we're left with x plus d over c times x plus b over a, and finally the final step is to slap the c up with the x and the a up the x, and we are finished. QED. Just another way of factoring that some students prefer, and therefore teachers should embrace the different methods teachers or students like to use in the classroom. I know the IB curriculum and the AP Calculus curriculum promote original thinking. Let's just hope the teachers do too. Keep your mask on, keep a safe distance, keep safe. Thank you very much.